Hello and welcome back to Data Science Castnet. We're going to do something a little bit different today. So I've just finished being a TA for the second year in a row for the Neuromatch Deep Learning course. This is a pretty intense 3-week summer school that covers a lot of deep learning topics. And so today we're going to try and sort of speed run this material. And if anything gets you interested, you can then go and check out the full sort of 3 weeks or more like 3 months worth of content over on the Neuromatch side. So, you ready? Let's start the clock. Day one is a simple introduction to PyTorch. PyTorch is a very flexible and powerful library designed around deep learning. It enables you to do lots of matrix operations on the GPU, and it also has built-in support for lots of layers and so on for building artificial networks. So artificial networks are these kind of amazing constructions. They are excellent function approximators. That is, given some input and some desired output, they are able to often learn the mapping from one to the other. So these are great. We parameterize them as usually lots of artificial neurons, each with some inputs and an output. But they're all sort of determined by these parameters, these numerical values that determine the behavior. So how do we set those parameters in such a way that this network does what we want? Enter gradient descent. If you can specify what you'd like, some sort of objective function, say we want to minimize some error or some loss, and then if you can find the gradient of that loss with respect to each parameter, that is, if I tweak one parameter, does the loss go up or down? Then I can use this information to update those parameters by some small amount to try and nudge them in a direction that reduces the overall loss. And if you do this multiple times, then congratulations, you are optimizing via gradient descent. So finding these gradients can be tricky. Fortunately, PyTorch does some amazing work behind the scenes to make this kind of seamless and automatic. So this is so-called automatic differentiation. And to do this, it keeps track of what operations have been done to each parameter, and then it's able to trace back through this sort of computational graph to give you the gradients using a mathematical operation called chain rule. So this is really great. This enables us to update a set of parameters to achieve some loss. How do we actually create that set of parameters? What is that sort of function or architecture? Well, this is typically some sort of neural network. And again, PyTorch has these lovely built-in sort of layers and nonlinearities, building blocks in essence that we can stack together. So we typically talk about deep neural networks as ones that have more than one hidden layer, right? Multiple layers where the output of one is fed into the input of the next layer. And by having this kind of deep structure, they're able to learn much more complex and interesting kind of hierarchical representations of data. And so this makes them really good for all sorts of useful tasks. So how do we train one of these networks? So using that gradient descent idea from earlier, we're going to do something like this, typical training loop. We will start by zeroing out any previously calculated gradients, cleaning the slate as it were. We'll then feed our inputs through the neural network to get our predictions. And we'll compare this with our target, right? Say a label for a classification task. And this will give us our loss. If we call loss.backwards, we're telling PyTorch to trace back through all the operations, which remember includes all of the layers in that neural network, and calculate the gradient of this loss with respect to every parameter that's involved. We can then use our optimizer to tweak these parameters, the weights of the neural network, to try and reduce this loss. And by doing this a number of times, we end up with, ideally, a network that's able to learn the mapping from our inputs to our desired targets. This optimization operation is pretty useful, but it turns out that vanilla gradient descent has its limits, right? It's talking about using all of the data at once, and sometimes it can get stuck in so-called local minima. So we have various improvements that have been made, and these are all covered on, I think, day 5, where first of all, we can process the data in small batches, small randomized batches. This means that we don't have to load all of our data into memory at once, which is useful when dealing with, say, millions of images. But that added randomization also helps with training. We can also add concepts like momentum, where we look at the previous update and use that sort of in a very physics-inspired analogy to modify our update so that we're not just looking at the current local gradients, but we can take into account past values. And then you also have so-called adaptive methods, which have, per parameter hyperparameters, right? How fast are we updating each parameter and so on. And these can help with badly conditioned problems and various other issues. A final note, and this is something that's covered every day at Neuromatch, is the ethics. And so it's a good chance to stop and reflect. We're trying to optimize some objective function, But choosing that objective function is important because if you specify it wrong, you may be either building in some sort of problematic biases to your model, or you might just be optimizing for the wrong thing, and your actual truly desired behavior will be suffering because of that. Another useful technique that kind of helps with the practical side of training these deep models is something called regularization. We tend to use a lot of parameters with deep learning, like way more than we might expect we need. And the idea here is that we will then reduce down the network's complexity somehow so that we kind of get this balance, right? This optimal capacity in the diagram here, where you have a network that's learned what it needs, but it hasn't just memorized all of the training data. And to do this, we use various penalties and other techniques grouped into this topic of regularization to try and reduce the model complexity, reduce dependence on any one sort of dimension of the input, and so on. And so in practice, this just means that the networks train more smoothly and tend to give us more generalizable results. Okay, moving on to more complex architectures. In week 2, we cover something called a convolutional neural network, right? So I have a cool visualization here, but the basic idea is that when you're dealing with something like an image, you might want to look for local structures and not really worry as much about position, right? You'd like to be able to capture these ideas more generally. And so in convolutional neural networks, you have these ideas of filters or convolutional kernels that are a set of learned weights, but they're applied repeatedly across the image in this sort of convolutional fashion, right? So that's one key idea. And then we have additional sort of dynamics like pooling and so on. But the core result of this is that we can share weights across space, right? We can have the same set of weights being applied to multiple parts of the image and giving us outputs accordingly. And so this is really useful. This turns out to have been the key to unlocking, especially processing of large images, because now we're not having one parameter for every pixel on the input, say. We could have a filter that doesn't really matter so much how large the input is. So for unlocking working with larger images and for being much more parameter efficient, these have been kind of the backbone of a lot of image and vision-based tasks in deep learning over the last decade or so. And then later on we can look at, in the course, some updates to this. So your sort of basic convolutional networking can only get you so far, right? So we have ideas like residual networks, which introduce these skip connections. And this enables you to have much deeper networks without some of the problems that usually plague deep networks, like gradient explosion or vanishing gradients. Right? They have these skip connections that give us a shorter path, a shortcut for data to flow through, and this helps us calculating gradients for those early layers. And then even on top of ResNets, more modern variants do additional tricks, like this ResNext architecture shown here, where you have sort of multiple parallel paths processing the data, trying again to be slightly more parameter efficient. This is important when working on, say, mobile devices and so on, but also just capturing more information for a given amount of parameters. Really, really cool style of network. And obviously there's thousands of different variants of these architectures, each with their own tweaks and improvements. And so there's a lot to go into there. Moving on from this, instead of treating this sort of thinking in strictly classification or image to desired target style deep learning, we also have a whole field called generative modeling. And the idea here is that we'd like to produce some data given a random input, right? We'd like to just produce this out of thin air, but we'd like it to match some training data. So for example, you have a data set of faces, you'd like to generate new faces that are somehow plausible given the training data, but also unique, right? So this is a really interesting class of problems. And to sort of build up to this, we start by looking at an architecture called an autoencoder. And this is any type of network that maps high dimensional input, and I'll use the example of images, but it could be anything, maps that down to a much lower dimensional representation, here H, the hidden representation, right? And this can be really small. And then you have a decoder side of the architecture that maps this hidden representation back to an output. So on its own, this is not necessarily a generative network, but it is really useful for things like compression. But you can imagine we're mapping our large inputs to this very small representation, and then the decoder is going from this representation back to an output. And so you might think, well, what if I give a random input as that hidden representation? So now this isn't derived from any input image, it's just a random vector in that same space, and I decode that. Will I get a plausible output? Well, the answer is probably not. But we can fix that. And so we introduce something called a variational autoencoder, which is a modification to that autoencoder structure, where instead of predicting a single point in latent space for that hidden representation, the encoder predicts a distribution. And then to decode, we sample from that distribution. So this alone wouldn't give us much extra, but we then impose this additional restraint. We use a second term in the loss function, apart from our reconstruction loss. We add this additional constraint that tries to compress this latent space, which forces the encoder-decoder network, this autoencoder, to learn much more meaningful representations, right? Because it can only work with some limited area in this latent space, and what's restricted to following some overall distribution, we might say. And so to do this effectively, it has to really be efficient with how it maps out that space. And in particular, this gives us a much more useful representation. And when we randomly sample from within this distribution, we tend to get more plausible outputs. So this is a much better generator than a simple autoencoder. Still, we'd like to take it further. So the next improvement then, or the next architecture rather, is something called a generative adversarial network. And this is actually two networks working in tandem. The generator is going to be producing outputs similar to the decoder side of the autoencoder, given random inputs Z. And then the discriminator is going to be fed both these generated images and some real images from our training data, and it's going to try and distinguish the two. So the discriminator is like a normal classification network, given an input and a label, real or fake, try and produce that label, and so we can train that. The generator is going to be trained to try and fool the discriminator. So it'll try and produce some images, the discriminator will learn to tell what's real and fake, the generator will try and produce even more realistic images to fool the discriminator. And so ideally, these two kind of work in tandem and get better and better and better over time. Now this has some issues. The generator doesn't necessarily learn the true distribution of the data, and you have something called mode collapse, where it maybe only produces a few plausible outputs, but that's enough to fool the discriminator. And there's many other issues that can crop up as well. Fortunately, we can have modifications where we either pass in some additional information, right, like a label, to both the generator and the discriminator, so that it can use this to sort of target in on specific types of image rather than trying to learn the whole distribution. So we'd call this a conditional GAN. And then there's also been various improvements to training objectives, strategies, and so on for reducing these problems like mode collapse. So these can be very useful artistic tools. I have here a site called Artbreeder that's got sliders that you can use to tweak and move in specific directions in the latent space so that the GAN output stays mostly coherent, but for example, you change the hair color. So that's very useful. And taking that even further, lots of different types of conditioning. We have a model from NVIDIA called GAN that you can feed in. You can see here a semantic map. You can feed in a text description. You can feed in a stylized image. And it'll take all of these inputs and try and produce an output that satisfies all of those. So the discriminator is trained given this map and this image. This is a true representation. And so the generator is trying to fool that. And so together they learn to use this conditioning information in a really powerful way. So really interesting field, lots more to study there. And then finally, this is not covered in the course, but there is one other class of generative model that's kind of stealing the limelight these days, and that's diffusion models. And unlike the others, this is a sort of more iterative process, right? We gradually corrupt our data by adding noise. It's sort of, you can think of it as a stochastic differential equation where we're adding noise, moving away from the distribution of the actual data. And then we try and learn the reverse of that process. So I won't go into that too much, neither does the course, but it is interesting because especially in fields like text to image, where you take a diffusion model and you condition it on some representation of a caption, we've seen really fantastic results where these are able to generate just amazing mind-bending images just from a natural language description. And there's lots of other applications that I suspect we'll see of diffusion models in the coming years. Okay, back on track. The next big topic is sort of sequence modeling, time series and natural language processing, because we often see data that isn't necessarily an image, which, a nice fixed grid of a certain size. Instead, we see data arriving, for example, speech, natural language tends to just be a sequence of, words and sentences, but you might also see, stock values or weather, time series, and so on. And so we need some new way of thinking about how we're going to process this sequential information. And one class of models that's historically been really good is something called a recurrent neural network, right? And so this network is going to be applied again and again as each new token arrives. but it's going to have some hidden representation, some hidden state, as it were, that it can pass to itself for the next iteration. So that's that H here you see. And so these networks are very useful because this hidden representation kind of captures the history of the sequence up until that point. And so they can handle very, very long sequences. And it turns out that if you train it right, that hidden representation can also just be a very useful representation if you then want to use that as a sort of input for your whole sequence that you can now use for classification or something like that. Really great class of model. But how do we work with something like words, which are just discrete entities, with one of these sequence models that still expects a numeric input X? And the answer is something called embeddings. So this is a very popular idea. We're going to take some sort of discrete tokens and we're going to map them into this sort of shared space, this embedding space. And this is the idea of an embedding. And so you can do this with a neural network. You can have just a learned table, right? Every word has its associated embedding. We often try and construct these embeddings so that this space is semantically meaningful. That is, two words that have very similar meanings should map to very similar embeddings, and two words that have very different meanings should be quite far apart in this space. And this is really useful. There's all sorts of interesting analysis you can do with these learned embeddings, where you can start to see not just similar words, but relationships between words, and they go into that quite deeply in the course. Another more recent architecture for dealing with sequences, and these are also sort of building on this idea of embeddings, is the transformer model. And so this transformer model uses this key idea called attention, where each token is mapped to an embedding first, and then that's mapped to a key, a query, and a value, right? And so the key is going to be used with the queries of the rest of the sequence, so we're feeding in the whole sequence, and the values of that whole sequence. And it's going to result in a new representation of that token that takes into account the context. So you can see here the token it, right, at the end of the sequence. What is it referring to? Well, it's the robot that's being mentioned earlier. And so you can see the self-attention is able to kind of incorporate relationships between words in this sequence. So this turns out to be very powerful. You can stack these transformer blocks on top of each other. And in fact, many architectures use one stack as a sort of encoder and a second as a decoder. And you can train them to try and predict the next word in a sequence. But to do so, they've got to learn these really useful representations. And it turns out that if we train a large enough network to do this task, you can unlock some really fantastic behavior. And these representations can be super useful for downstream tasks like classification, summarization, translation, and so on. So this is really the sort of cornerstone of modern natural language processing, this transformer architecture. Again, lots more information in the course. Okay, second last topic, self-supervised learning. So we've already seen a sort of example of this with the language modeling that I just described. But what is self-supervised learning? Well, it turns out that labeling data can be really time-consuming and expensive, right? When we were talking about the convolutional networks earlier, a common data set for that is ImageNet. It's like over 1 million labeled images. But scaling up this kind of data can be very, very time-consuming. And in general, the more data, the better, right? The more data we have, the better the representations we can learn, the better performance we'll get on different tasks. So how do we generate more training data without manually annotating it? This is the domain of self-supervised learning or unsupervised learning. And so in self-supervised learning, what we're doing is we're finding some training targets and training objective that we don't need to manually specify, right? We can derive it from the data. And so a good example of this is the so-called SimCLR structure, where we take an image and we can create two versions of that image, right? And we can do this automatically through random transformations. So those two different versions of the image are both going to contain, in theory, the same idea, right? These are still both going to be images of a dog. And so if we'd like to learn a representation that captures this dogginess, but is able to be robust to different sort of rotations, transformations, etc., we can use this contrastive loss, whereby we try and maximize the similarity between these different versions of an image, because we know they contain the same thing, while trying to minimize the similarity between these images and lots of other unrelated images. Right, so we're going to take a big batch of images. One is a dog, one's a cat, one's a car. We're going to map these all into some embedding space using something similar to the encoder of the autoencoder we saw earlier, right? Some network that feeds out an embedding. And then we're going to look at the similarities between different pairs, and we're going to try and increase the similarity between ones that should be similar and decrease the similarity between the rest. Very, very powerful structure. And what we end up with from this is a way of having these representations that are kind of invariant to different transforms. So you can look at, here we have 3 versions of a car, 3 versions of a dog, and we'd like the similarity between these different image pairs to be high for the different versions of the dog and low for the different versions of a car. This is called a representational similarity matrix, really useful tool for exploring what exactly a network is learning. And so this was covered under this umbrella of self-supervised learning. And it turns out this is a really powerful technique. Modern day self-supervised networks are able to learn on mostly unlabeled data and then take very few 5, 10, 50 labeled examples and achieve performance that's comparable to the best supervised approaches from just a few years ago. Really is a fascinating field, and I think more and more as our demand for data increases, this is going to become more and more popular as well. Okay, final topic goes into a slightly different area of deep learning, this idea of reinforcement learning. Now we are not just trying to passively classify or process data, but we need to learn to act and interact with an environment. So we have this model here. The environment is going to be some sort of world. You can think of like a game board, for example. We will see what the current state is. That'll be our observation. And then we'll try and determine what action we should take. And at some point we might get some reward, and the goal is overall to maximize this reward. So where deep learning comes in is that in many cases today we use these neural networks, these efficient function approximators, to model various components of this system, right? Either to estimate which action might be likely to be taken, or just to look at a state in the environment and say whether or not this is desirable, and to try and sort of forecast what potential reward we could expect from different states. So these are 2 sort of approaches. Value-based, given a state, estimate the value of your future reward, and you can discount rewards that are far in the future to try and focus on more immediate rewards. And so this is useful if you want to use this to say, how do I actually act then with this network? You can say, well, I can see what possibilities I have. I could go to this state or that state depending on my actions. Which one is going to give me a higher reward according to this network that I've trained? I'll choose that option. There's a trade-off in reinforcement learning, which is to say if you always choose that option, you might miss things that could potentially be even better. And so especially initially when your value function is not really good, it hasn't been trained yet, you would like to sometimes take random actions to try and explore the space a bit better. And so we usually have a little parameter epsilon for how much exploration we'll do versus exploitation, just looking at the best action according to our current estimates. Another variant is to, instead of trying to learn the value function, just look at a state and try and learn what the best action would be directly. And this is often done in sort of combination with behavioral cloning, where you start with, say, a database of games that have been played by a human, or some sort of group of experts, right, have sort of ranked this is the best action or this is the action that the expert took. And so the network tries to learn to imitate that. Given a state, try and predict what a grandmaster would play, and then we can use this to determine our actions just by looking at which ones the network thinks are more probable. Again, you can trade off exploration versus exploitation by maybe not just always going with the most probable action, but sometimes choosing one of the others instead. And then all of these ideas can kind of be merged together. So you can look at the policy network with also a value network to estimate things. And then you can add, if you're feeling really fancy, some idea of planning where you simulate sequences of actions into the future, informed by your policy network and your value network. And then you see after 10 steps ahead, 50 steps ahead, which one actually leaves me better off. And then you take that sequence, you pursue that sequence. And so this is what's used by, for example, AlphaGo, AlphaStar, etc., to do these amazing feats of game playing. And then they're learning all of this. They're playing against themselves to improve their value function estimates, their policy functions, and so on. Really, really fascinating field. Okay, stop the clock. I think we're at about 22, 23 minutes. Hopefully you feel something like this. But as I said, we're just skimming over, taking a very bird's eye view. But if anything here sounds interesting, you can now go look up the deep learning .neuromatch.com or IO, I think. Go look at the material, dig a little bit deeper. I hope you've enjoyed this. It's just my attempt to kind of give an overview of, like I said, a very intense 3 weeks of learning. Thank you so much, and we'll see you in the next one.